All right, let's get straight into it. We are about to lay out the blueprint for a record-breaking electric race car. With over 2 decades in this sport, I've seen so many brilliant teams make the same early mistakes. This right here, this is the strategic guide I wish they all had. It's a way for a brand new university team to think and build like a world-class competitor from day one. So let's start with a question that honestly sounds a little crazy. How on earth can a group of university students in a campus workshop build a machine that accelerates faster than the absolute pinnacle of motorsport? It seems impossible, right? But the world record for 0 to 100 kilometers per hour, it's held by students. So the question isn't if it can be done. The real question is how do they do it?
Well, the answer isn't some tiny secret tweak or a magic part you can buy off a shelf. It's a huge, foundational, strategic decision that you have to make before you even sketch a single component. You have to commit, right from the start, to a high-voltage, 600-volt architecture, and you have to pair it with a four-wheel drive system. That's it. That's the core of this entire strategy. So what we're talking about here is much more than just picking good parts. This is a strategic choice to completely leapfrog years of slow, painful trial-and-error development. The whole idea is to intentionally sidestep the common pitfalls and build a car that can go head-to-head with the absolute titans of the sport. We're talking teams like ETH Zurich and TU Delft, from the very moment it hits the track. Okay, so these are the numbers that define a winning car. And these aren't just random goals. They're reverse engineered from years of championship data. You've got a system voltage pushing that 600-volt limit. That's for maximum efficiency. Peak power is capped by the rules at 80 kilowatts, so we'll take all of it. Over 1,200 newton meters of torque to absolutely shatter that 2.5-second barrier. It may be the most important number, total vehicle mass under 200 kilograms. It's that combination that gets you to the holy grail, a power-to-weight ratio over 400 kilowatts per ton.
So why are these two decisions, high voltage and four-wheel drive, so absolutely critical? Well, because this isn't about style or preference, it's about pure physics. We're literally engineering an unfair advantage right into the car's DNA.
Now check this out. It all comes down to the simple, brutal math of electricity. Remember, power equals voltage times current. And since our power is capped at 80 kilowatts, if you double your voltage from, say, 300 to 600 volts, you get to cut the current in half. But here's the real magic. Heat loss, all that wasted energy, is proportional to the current squared. So having the current doesn't just have your losses, it quarters them. A 75% reduction in wasted heat means you can use lighter wiring, you need a smaller cooling system, and way more power actually makes it to the road.
And that brings us to the second part of our unfair advantage. A rear-wheel drive car is always going to be limited by its rear tires, but a four-wheel drive car, its secret weapon is something called torque vectoring. By precisely controlling the power to each of the four wheels independently, you can create an extra turning force, a yaw moment, that literally rotates the car through corners faster than its tires alone should allow. Oh, and you also get to recapture braking energy from all four wheels, which is a massive bonus in that long 22-kilometer endurance event.
All right, with our core physics advantage locked in, we can move on to the heart of the car, the battery. And let me tell you, this is not just a box of cells. This is the most technically dense and critical system on the entire vehicle, and the strategic choices you make here are everything. So here's the absolute key to battery strategy. For a short 22-kilometer race, you don't need a marathon runner's endurance. You need a sprinter's explosive power. And that means we need to prioritize what's called power density, the battery's ability to discharge its energy incredibly quickly, over energy density, which is just the total amount of energy it can store. It's about the sprint, not the marathon. And that one decision leads us right here. You see, while cells like the Sony VT6 are a proven choice and the Samsung 25R is super lightweight, the Molicel P45B is the clear winner for our strategy. And why is that? It's because it has an extremely low internal resistance. In simple terms, that means when you demand a huge burst of power, the voltage doesn't sag, and it generates way less waste heat. It is the sprinter we've been looking for. And here's exactly how we stack those cells together. We'll use 420 of them, configured as 140 in series and 3 in parallel. Now that 140 series number, that is one of the most critical details in this entire blueprint. The rules say you cannot exceed 600 volts. Ever. A lot of teams build a 144 series pack, but its fully charged voltage is over 604 volts. That's an instant disqualification. This design bakes in a professional 12-volt safety margin. You will pass tech inspection every single time. Okay, so our energy source is locked in. The battery is ready to go. Now,
How do we convert all that potential into 80,000 watts of controlled violence and truly record-breaking speed? The choice here is pretty much the industry standard, and for good reason, 4 AMK DD5 in-hub motors. But look at that number, 20,000 RPM. That is just screaming fast, and that incredible speed is what allows the motor itself to be small and light. All that speed is then converted into massive torque right at the wheel through a beautiful little integrated planetary gearbox. So we have these 4 incredibly powerful motors. But how do you actually orchestrate them? What's the critical link that takes the battery's raw DC power and feeds the motors the perfectly controlled AC power they need? And more importantly, how do you do it with almost zero waste? The answer lies in this number, 99%. That is the insane efficiency you can get from a modern inverter that's built with a game-changing material, silicon carbide. So why does a 99% efficiency matter so much? I mean, what's a few percent? Well, a 3% gain over older tech means 3% less energy is just burned away as useless heat during that long endurance race. And that directly translates into needing a smaller and therefore lighter battery pack to finish. Saving 2 to 3 kilograms might not sound like a lot, but in motorsport, that's an absolute eternity. And that brings us to our final section, which you could argue is the most important of all. You see, all the hardware we've chosen so far, that just gives the car its raw potential. But it's the software, the code, that actually unlocks its winning performance. This is the real secret weapon. At the very center of it all is the Vehicle Control Unit, the VCU. It is, quite literally, the brain of the car. It's what runs all the complex algorithms that make everything work together in perfect harmony. Things like traction control to prevent wheel spin, and that magical torque vectoring that turns our four-wheel drive system into a cornering monster. It's the invisible hand that guides the car to its absolute physical limit. But this brings up a huge question. Let's be serious for a second. A 600-volt system is incredibly dangerous, and complex software can and will have bugs. So how do you make absolutely sure the car is not only fast, but fundamentally safe and reliable? The answer is process. A rigorous process. You adopt the exact same V-model development process used by the world's top automotive companies. And the most critical step is something called hardware-in-the-loop testing. This is where you connect the car's actual brain, the VCU, to a powerful simulator that tricks it into thinking it's driving on a racetrack. You can push it to its limits, you can simulate every possible failure, and perfect the code in complete safety, long before that 600-volt system is ever switched on for real. And then, layered right on top of that software process, you have these non-negotiable hardware safety systems. Think of them as digital seatbelts. The insulation monitoring device is like a smoke detector for any electrical faults. The high-voltage interlock is a physical safety loop that makes it impossible to touch a live connection. And the brake plausibility device is a fail-safe that instantly cuts power if the brake and throttle are ever pressed at the same time. So when you put it all together, you see how these 3 pillars support each other. The aggressive 600-volt four-wheel drive hardware, that gives the car its raw potential. The advanced software, like torque vectoring, unlocks its ultimate performance. And the rigorous V-model process ensures it's all done with absolute safety and rock-solid reliability. And that really brings us to the final, most important takeaway. This document, it isn't really about building a faster car. It's about creating a better process and building a stronger team. By following this blueprint, a new team doesn't just build a machine, they build a culture of excellence. And at the end of the day, that is what truly wins championships.